So good afternoon, everyone. My name is Annie Wong. I will be your moderator for today. Please keep yourself muted throughout the presentation, and you may enter your questions and comments into the comment box. Before we start, I have a couple of announcements from the Southern Alberta ITE. First, our next webinar in June will be on the Deerfoot Trail study. And please also save the date for June 8th to 10th for the CITE Virtual Annual Conference. Registration is now open. And there are also 2 more transportation equity listening sessions on Thursday, May 27th and Wednesday, June 30th. So without further ado, let me introduce our speakers today. We have 2 groups of University of Calgary students today here to present on their engineering group projects. First, we have a team presenting on designing safe and efficient public transit system in response to COVID-19. Their team members include Ella Shakula Ross, Oji Adahosa, Barney Mel, Dominique Ambrose, Corey Drake. And we have another team presenting on autonomous mobility on demand. And their members consisting of Anastasia Alexieva, Nasir Ahmed, Hamza Naeem, MD Asif Shahira, Marvik Hambi. So without further ado, let's welcome our first group for a presentation, and they will be presenting on autonomous mobility on demand.
Let me just share my screen here.
There you go. I think
So it's not letting me share.
Oh, sorry.
Yeah, the button is like grayed out. There you go. Awesome. Share screen. Okay, can you guys see my screen?
Yes.
Cool.
Okay, I think we can get started. Well, hello everyone. Thank you for joining us for the presentation of our capstone project, Autonomous Mobility on Demand. The team that completed this project, as Annie introduced, is myself, Asif, Marvik, Hamza, Nasser, and Anastasia. And throughout this project, we were guided by our academic advisor, Dr. Lena Katan, and our industry advisor, Ryan Martinson from Tool Design. Next slide. So the agenda for today includes an introduction to our project, our pickup and drop-off street designs, MatSim testing, street network final design, a cost-benefit analysis, and our conclusions. Next slide, please. So I'll be going through our project objective. So the objective of our project is to study the impacts of autonomous vehicles on downtown Calgary in the year 2070 and provide recommendations that make the most of the inevitable effects it'll have on the transportation network. Our project began with creating a base simulation. This allowed us to verify the accuracy of the simulation we created. We compared our data to Caltrac's data that was available on the City of Calgary website. We then utilized this calibrated simulation and imported forecasted trip data from Alberta's Department of Transportation. Using this data, we ran multiple scenarios with different parameters to extract meaningful and useful data. This data was then analyzed to design safer streets for road users, create a more human-centric design, and a more environmentally conscious transportation network. My colleagues will further discuss each major component of our project in more detail. Next slide, please.
Hi there. So the first component of our project was creating or designing curbside improvements known as pickup drop-off points, which essentially provide a safe and efficient way to pick up and drop off passengers. They allow for the grouping of trips in a semi-transit system that reduces traffic and encourages more walkability, specifically in space reclaimed from parking lanes. Through our project, 4 different PUDA street designs were created. Next slide, please. Our first design was the PUDA lane, or essentially a use change from parking to pickup and drop off. This would be the most versatile and cost-effective method. Could be rush hour lane during periods of high traffic and a social space in periods of low traffic. However, there were some, again, safety concerns, specifically with using it as a social space, and there was a possibility for more space reclamation when we did our simulations. So let's go to the second slide. Next slide. This is our second design, the multimodal corridor, which is essentially we've reclaimed the driving and parking lanes for walkable and pedestrian space. A multi-mobility path for bikes, scooters, skateboards is added, and to encourage these healthier and more human scale modes of travel. Again, this is a bit more costly to implement and requires a drop in flow volume, which we actually did see in our simulation, which we'll talk about a bit later. Next slide. Our next more human-centric, more human level pickup drop-off street design was a shared street where essentially the road and the sidewalk would be merged into a curbless street, and the entire space is sort of available for public use and for pickup and drop-off. Again, with the pedestrians having the right of way over all of the modes. This was achieved due to a large drop in speed, something that's more a parking lot level, right? Less than parking lot levels, and this could of course excessively harm the utility of other modes of travel. So we use this sparingly in our simulation, but still quite a bit. Next slide. The final, our mostly completely human-centered street is a parkway, which is essentially a vehicle-free street where the street is entirely reclaimed by walkable or green space. There could be paths of active travel, playgrounds, and social spaces, as well as stores and extensions of private property of some sort, creating again a completely human-centered street for pedestrians and maybe completely human-level active modes of travel. Again, this is the least feasible and most costly to implement, but we were lucky in our simulation, which we'll talk about after this, that we were able to implement all 3 of our very human-centric designs: the parkway, the multimodal corridor, and the shared street. And we'll talk more about that right now. I'll pass it off to Marvik, I think.
Thanks, Nasser. Now I'll be talking about the background work that played a very crucial role in our project, and that is the MathSim software. Without going into too much detail, MathSim was utilized to iteratively produce a simulation that will analyze the behavior of Calgary's road network system with the presence of autonomous vehicles with the help of 2070 OD matrix data projection by the Ministry of Transport, transit data schedule from Calgary Transit website, and also road network properties from different sources like City of Calgary database, Google Maps, and OpenStreetMap. We were able to produce a simulation that would resemble Calgary's road network system in the future. So here's a short GIF of our simulation. So metrics such as total person hours traveled, average trip duration in the system, distance traveled by mode, and total reclaimed space were extracted from the results of the simulation and are then used to evaluate the effectiveness of the design. So for our simulation, our geographical boundaries are as follows. We have the Bow River for the upper boundary, 17 Ave for the lower boundary. We have 14th Street for the left and Elbow River for the right. So all major roads within these boundaries were considered. Now I'll pass it to Anastasia, and she'll talk more about the design process on the next few slides.
All right, so we used a variety of ArcGIS software layers to create this map that basically had all these numerous factors which would affect our pickup drop-off point placement. So our initial map related to our base simulation, and we used public transit location, the +15 map, and these connector links and nodes that showed trip concentration so that we would be able to map out our initial preset design. And as Marvik mentioned, we performed iterative testing by changing road conditions wherever we saw a PUDO zone fit, like the pickup drop-off zone fit. And then we compared those results to our updated simulation and back and forth like that in an iterative process. So our final optimized solution, as you will see in a bit, it includes the aforementioned multimodal corridors, the shared streets, and the parkways, all utilized together with proximity to public transit, +15x space, and park space, green space. So our first street network design, the layers that we obtained were current volumes from Caltrax and the bike lanes, just so we can get started. Our next one is public transit. So we mapped out the C-train lines as well as the bus stops that we wanted to base our PUDO zones off of. So the next one, it's just a whole bunch of other layers that we obtained. Some we made our own, some we obtained from the city of Calgary. And basically, this is essentially showing the different +15 entrances, concentrations of retail and business centers where you would expect more people, and just green space, as well as the connectors which showed trip concentration. Our first network design, and this was kind of our first draft, so this was based off of our initial base calibrated simulation. And the thick graded white lines, they show that the shared streets, so the PUDO vehicle can essentially, or the AV can essentially stop anywhere along those shared streets, whereas the icons, they show multimodal corridors, so specific stops along higher speed streets. And this was our initial design, so the next one will just be our final design. And then we also included the radius or the reach of a specific multimodal corridor PUDO point. So that way that people who get off at that specific point don't have to walk too far. It's the max they have to walk is 420 meters. So we just wanted to make it more accessible in that sense. As well as you can see that we added parkways. So like Nasser mentioned, the vehicle free zones. And the next slide here is our final map design. So this just shows a more cleaner version of the previous one without the encompassing radius. And yeah, so that's our final network design for pickup drop-off points. And then this last one is we wanted to also consider storage and protection of the vehicles. So we are essentially converting City of Calgary parking lots to these depot points, which is just where the vehicles will be stored and charged in a warehouse while they are not in use. So in our next slide, we have 3 case studies that we wanted to show. So how essentially we would convert the current street layout to what we want it to be. And this is 6th Ave Southwest. We actually use Street Mix to model what it currently looks like, sort of based on similar widths and what we have there as a cross section. And for multimodal corridors, this is what it would look like if we were to retrofit the street to actually have that space for a division of high-speed vehicles versus active modes, while still keeping the waiting stops there for multimodal corridors. So our second example is 10th Ave Southwest, which is what we would think would be converted to a shared street. This is the previous cross-section of it that we have. So you can see that it's based off of the Google Street View. And this is our final one. So we can see that there's more green space, more focus on active modes, and just ensuring that the AVs have a lower speed along those streets. Now our third example is 8th Ave Southwest. So that's currently what looks like a shared street, but we want to go further and make it more human-centric. So we're converting it to a parkway. Our previous cross-section resembles similarly to what you just saw in the Google Street View. And our after, you can see that there are no vehicles. There is more greenery, more active modes, and just more community gathering in general. So I will pass it to Hamza so he can speak about the design implementation of the costs and the analysis of our networks.
Thanks, Anastasia. So we approach cost evaluation through a number of different methods, including research of unit costs and literature like the City of Calgary Complete Streets Guide. We also looked at previous projects such as the Calgary Bike Lane project. And overall, our capital cost was estimated at over 270 million. When it comes to the maintenance costs, we use data from transportation agencies, and this is what we came up with, which is over $300,000 in annual maintenance costs. The cost estimation was very high level, so given it wasn't the main focus of our project, so there's likely a lot of uncertainty associated with that. When it came to the cost benefit, so our benefit analysis for the implementation of these autonomous vehicles was approached by looking at a number of different impacts, but which included like vehicle kilometers traveled, increase in green space and active mode promotion, but we decided to go with safety and accident reduction, just because this was something that had a lot of research behind it. And basically we used Kara Kokelman's research to base our assumption that autonomous vehicles would reduce crashes by 50%. And based on that, we came up with annual saving of over 79 million. And then our cost benefit analysis concludes that in the fourth year of our project, we would recoup the capital costs. Next slide, please. So to summarize our project, what we did was we designed some PUDO points. We mapped out their location in our network and optimized those locations. So this was overall, it was an iterative process with many variables. What we ended up with as our results was the cost benefit analysis I just discussed. Another one of our main results was the reclaimed space in our optimized model, which was over 350,000 square meters of that walkable and green space. And our final model also yielded higher walking kilometers traveled, lower vehicle kilometers, and system vehicle hours traveled. We were also able to relieve congestion, which lowered the average trip duration. Overall, we identified many benefits that we looked at qualitatively in a more like holistic approach. So these center around our original principles of livability, equity, and sustainability that we were going for in our project. So based on the recommendations from our advisors, we assume zero emission vehicles for our network, which is an obvious environmental benefit, along with that increased green space. Adding to the livability aspect is the promotion of active modes and improved air quality, leading to a more human-centric society. Lastly, the use of shared AVs as a carpooling service leads to a more equitable access as the privatization of vehicles was removed. And yeah, that's the conclusion of our project. I don't know if there's any questions.
Thank you. I think we'll have the second team to present first, and then we'll go through all the questions at the end.
Okay.
So now we'll have the second team presenting on design safe, efficient public transit system in response to COVID-19. That's Barney.
Is it possible to have Ogosa share his screen now as a presenter?
Sure. Okay. Can he turn his webcam on so I can find him?
Sorry, I'm trying to. For some reason, it's not letting me turn my camera on. Give me a second. Let me.
Oh, there you go. I found you.
Oh, perfect. Okay. Can everyone see the screen right now? Okay.
Yeah, looks good, OG.
Yep.
Thanks. I will do this here. So hello everybody. We are the COVID-19 group, like we're the transportation one group of the capstone this year, the civil capstones. And our project name was to design a safe and efficient public transit system in response to COVID-19. So this is the agenda for today. We're going to sort of go through a more brief look into our project and what it entailed effectively. And if you have any more questions for us at the end, we can talk more about that. So first, we're going to talk about what is the capstone, what is the NCI 570. So at the U of C, if you're in the civil department, you have a few choices in terms of what your capstone can look like, or what your final year project can look like. You can take an entrepreneurial route, or you can take a multidisciplinary route. The NCI 570 is a specifically civil-focused approach to the capstone. It is a year-long focused design project where we take all our previous knowledge from all the previous years and I tend to apply to a real-life sort of industry problem where we work with people from industry and we work with academic advisors, and it sort of culminates in this big capstone presentation and project where we get to sort of talk about our work and show what we've done so far. The project scope and goals. The entire sort of goal of our project was, we all understand that the COVID-19 pandemic has affected the world in a plethora of ways, from the health of the public to the state of the economy, all the way down to the way people work and interact with each other. So one of the biggest sectors impacted by this, of course, is the transportation industry and the transportation sector, especially with public transit. And so the goal of this project, with the increased apprehension towards taking transit, was to find ways to improve the safety of transit use, as well as to sort of entice people and improve their peace of mind so that they have a better understanding of the things that work within the transit systems in the process. So we sort of have our scope reaching towards the train stations themselves, the trains, and then some of the different layers around that, including like the different buildings and how they interact with each other. Our final design here is based on a simulation and a cost-benefit analysis. So in the design process, the very first part of our design process was trying to decide what station we would pick to design, because ultimately we couldn't design the entirety of the city. And so in this case, we picked Marlborough Station because it is a station that effectively mimics more of what appears in Calgary, in a city like Calgary. And so by picking that station, it makes our designs more applicable to a broader range of stations within the city. And this is a decision matrix for how that decision was made. So this here will further explain the rest of our design process. So we went through a number of alternative designs, and we had a design analysis using our simulation and our cost-benefit analysis, and then we chose a final design afterwards. So in terms of alternative designs, we had a number of short-term and long-term designs to come up with. And not all of these were implemented, obviously, going through the process. But we had the decals. So the idea of using decals to indicate directional flow is, if you can see my cursor, this sort of an idea. We had barriers like this here. So the idea of sort of separating flow in itself, boarding and alighting demarcation, which you can't see on here, but it was another idea of effectively dividing the train platform itself. And then improving the app usage, which is something we investigated highly, and because we found that there might be bottlenecks in terms of waiting for tickets and validating tickets and things like of that sort. So if we improved app use, it would actually increase flow through the stations themselves, and actually reduce the amount of times people have to interact within the system. And then we had longer term solutions like physical barriers, wider walking areas, which would involve full-on reconstruction of certain platforms in certain areas, the platform shelters, and door sensors, which was a technological decision we thought would be interesting to see what would happen if we could have the doors sort of sense the trains themselves sense the number of people in them, and then the station itself sense the number of people in it, as well as open and close depending on what was needed.
Okay, thank you, Oji. For the simulation, in order to simulate our designs or get a better idea of how effective they are, we use a software called PTV Vism or VisWalk, which is a pedestrian modeling software. In this case, we implemented the broad design concepts we showed in the previous slide, most of them, and the ones that were not implemented were only not because it was not really possible to do so. For example, if we put more signage or decals on the station, those type of things were not really, the effects of those methods were not really apparent in the simulation model, but other things like widening the paths were implemented. So also during the PTV Vism, for the first few weeks or months of our project, it was really an iterative procedure of trial and error to see which designs were able to be implemented and which were not. We also, on this page, you can see the bus and train properties where you can modify them on the PTV Vism software. You could notice that you could change the speed of the vehicle when it's arriving at the destination. You also could add in a variance or a distribution of time. So in this case, we, for the trains, for some of the scenarios, we did a plus minus 20 seconds, and that really depends on the scenario we're going to, we analyzed. And you also could set the schedule and the schedule of the vehicle when it's arriving at the station, like when specifically the headways between each arrival, along with the occupancy. And later we tried to test the walking behaviors of pedestrians in the software, and you could do so by changing the A social mean or B social mean numbers by trying to vary the numbers. There's sometimes some weaknesses in the software where if you change the number a bit slightly, the people might fly off the simulation, which is not realistic and undesirable. So that's another point of a lot of iterative measures we took in seeing if we could play with social distancing or other measures like that. Next slide, please. On this one, you can see the pedestrian composition. In this case, for our models, we use normal pedestrians and we added in some wheelchair users. The wheelchair users, the volume of them are only a small component of the regular pedestrians. And we added them just to simulate or show what happens if there's wheelchair users at the station and to cover more of the possible pedestrian compositions at a realistic train station. You also can see on the right-hand side, the pedestrian routing decision, partial or static routes. The main point is showing this is because we had to sometimes, when we made all these different routes or potential routes the pedestrian could take, we had to, you could see under pedestrian classes, when it says all pedestrian types, it means this specific route is being a possible route that all the pedestrian compositions could take. But some routes, like for example, for wheelchair users, it might not be realistic for them to go down on normal stairs, and it would be more realistic for them to go through the elevator. So for those types, we had to make some small changes, or else to match the more realistic behaviors. Next slide, please. In our scenarios we modeled 5 of them, which the first one being the base model of Marble Station, second one being widened paths model, and then the split widened paths model, the escalator only design model, and the split path escalator model. And of these, we'll show you, we'll show you them later. Yeah. So of the simulated designs, we did a base case, and the base case is based on the current data provided by Calgary Transit. And then the worst case is based on the peak hour flow of a station currently. And in this case, you could see we put at 40 passengers per train with headway of 3 minutes for the train, and then 15 passengers per bus with 3-minute headway for the buses. And then the other pedestrians, like from the sidewalk or other businesses near Marlborough, would compose 25%. And then the future expected case is almost the same, with 75% of the numbers for the train and bus passengers. Well, some variance is added in the headways for the future expected case, and the variances, for example, for the train are like 20 seconds, while the ones for the buses are 30 seconds. And the reason for that is we just thought it would be more likely for traffic jams to occur on the road rather than delays on the LRT station, but that's one of the assumptions we made in the end. Next slide, please. So now we could go to the simulation demo. So Uchi, could you? Yeah.
I can pull this up right now. And go ahead.
All right, so now you can see our base model that we based all our designs on. Our first step was to make a base model of the current station without changes being made. And you can see here all the pedestrians moving through the whole station, and you can see the both sides. If you are familiar with Marlborough, you might see some familiarities with this. In this case, you can see when you go to the bus station, you can see how the software could show the loading and unloading of pedestrians at bus stations, and then you can see pedestrians coming from sidewalks nearby the station, and they're all the whole system is being shown here. I'll mention some limitations of the software. So one of the limitations, you could go into the circular ramps. At Marlborough Station, it's a series of multiple ramps, like a helical shape. It was very difficult to actually draw the helical shape in the model, so we had to simplify it slightly. And this assumption wouldn't really impact the validity of results in the end, because it's kind of a constant assumption. And if we, for example, did several changes for widening the paths or adding an escalator, the effects of those decisions would still be valid as the assumptions kept constant, so it's kind of negated a bit. If you could go to the stair area. So right now, this is the right now situation of there's stairs like of the Marlborough Station, but some other models that we developed several more that are not being shown right now. For example, you could destroy half of these stairs and add in an escalator to see the effects of them. And that's called the escalator only case that we showed earlier. And we also could expand the paths for the pedestrian cross bridges. In this case, you can't really notice it, but you could change the width of it in the simulation model. And yeah, this model also could be able to get data results from it, and these data results were used later in our analysis to see the effectiveness of each design that we made. And now we can move on to the next one, OG.
Yep.
Yep, sorry.
I've got to move it and stop it. Yeah, ignore and back.
Okay. All right, other than the simulation, PTV simulation, we also explored on-demand seating reservation system, as previously mentioned. And we also thought about the potential implementation of machine learning or mask recognition at a train station. And this could be implemented or integrated in any design, really. And this is the one you can see on the screen is basically testing it on myself. The interesting thing about machine learning is you could test it on many different applications. And in this case, you could even test it on your own pets. So if you want to try something in your spare time over summer, you could try cat dog recognizer, and that's basically the basis of many of these things. But going back to this, the point of doing this is to show another solution of helping to ensure that proper safety protocols are being followed at this train station. Next slide, please.
All right, thank you, Barney. So we also created some detailed and accurate renders of our designs in order to kind of determine the physical feasibility of our designs, as well as to provide a visual aid in describing what we're simulating and also kind of just connect it to reality, because it's kind of hard to see what's going on exactly when you have all these boxes and not all the walls in the actual simulation. Next slide, please. So here we have our cost-benefit analysis, and this is the modeling of the risk analysis, for the infection risk. And we took a modified version of the Wells-Riley equation. It was originally modified by Zhou et al., but we modified it further to suit our scenario. And all these variables have to do with the population that's masked, that's not masked, the probability of infection for a masked individual or a non-masked individual, and then just particulate matter in the air or air droplets of an infected person in the air. And if you go on to the next slide, we calculated the yearly cost to society by taking the unemployment rate, or not the unemployment rate, sorry, the unemployment yearly cost and the hospital stay yearly cost. And that was our yearly cost to society per infection. And we had to make a bunch of assumptions because there are hundreds of variables to calculate and take into account when calculating the cost. So we didn't calculate things like surgical cancellations or other costs due to COVID-19, but they're not impacted by the multiple design options of the Marlborough station. And I will pass this on to Corey.
Thanks, Tom. So the ultimate goal of our final design is to reduce the risk of infections for passengers of the transit system. However, as in any engineering project, the financial impact must be considered also. So using data collected from the cost-benefit analysis, a ratio of capital cost over cost to society was calculated, with a number as close to zero being desirable. And interestingly, the more simple options that we considered turned out to be the more cost effective. So the final short-term option we came up with was just the split path. And the long-term option was the widened path. Why is it important? So we all know the effect the COVID pandemic has had on the world, and you can see the daily active cases in Alberta up to April 6th on the screen. And even with vaccine coverage on the horizon, it's important to better understand passenger behavior. And additionally, it's possible that another pandemic could happen in the near future, according to experts in the field of epidemiology. So it's crucial to understand how to mitigate the effects on the transit system as best as possible. And by understanding passenger movement on a granular and macro level, we can find answers to other questions in the process in terms of the best way to move people around. If you're interested in knowing more, you can visit our website, and you can see it here, which we created for the Engineering Design Fair. And if you have any questions that you'd like to ask after the presentation, you can contact any one of us at our emails listed below. And that's pretty much it for our presentation. So thank you for listening, and if you have any questions, don't hesitate to ask.
Awesome. Thank you. Thank you to both teams for their very innovative presentations. And now we'll begin our Q&A session. If you have any questions, please type them into the chat box. I think I saw here one earlier from Saeed. He had a comment for very impressive work on 8th Avenue. There are many restaurants and shops. How delivery trucks or emergency vehicles access will be handled in the new design. I think this is for the first team.
Yeah, so thanks for the question and thanks for the appreciation of our presentation. I think the biggest thing that we're using for this problem, right, is existing shade streets or existing parkways. For example, 8th Ave, if you just is actually an extension, right? If you just keep on going, you run into Stevens Ave, right, which is essentially a walkable street, a very walkable street. And to service Stevens Ave, right, there is one lane for delivery trucks, and the hope is to at least leave some walkable space or some in terms of active mode space in shared streets and parkways, so that delivery trucks or emergency vehicles can at least come in and drop off or do what they need to do. There will also be the assumption, of course, is that with the very with with sorry that there will be I'm just have to look at this right now, a traffic management system, where essentially you'd have to like book in your time that a delivery truck will go in to ensure that only one vehicle or the at a time can be in that block, essentially so that they don't take up too much space. And yeah, if otherwise back alleys, other intersections, just a lot plethora of different solutions will be used to handle that logistical problem, right? Could be in the future again, where could be autonomous robots, something like that. But yeah, the assumption is there will be enough space for at least one delivery truck or one emergency vehicle, and if there needs to be more, then on the parkway, right, there's gonna be grass, like there's nothing stopping an emergency, like a fleet of ambulances or police cars to just drive over the grass and reach the location, right? But again, like I said, there's gonna be hopefully enough space in the real application of our design to handle these problems.
Thank you, Nasir. We have another question. I think it's also towards your group. Where were the 3 Poodle locations you recommended?
Okay, so I think if you're referring to the 3 examples that we showed that were 6th Ave, 10th Ave, and 8th Ave, those were just, so the 6th Ave is just between, I believe it's 3rd and 4th Street Southwest. 10th Ave is around 1st, 2nd Street Southwest, I believe. And then 8th Ave is just somewhere around 3rd Street Southwest or something like that. But in general, all those different types, those were just like case studies that we showed. So the multimodal corridor, the shared street, the parkway, they're all over that map that we had basically, which was, it was like that map showing those kind of whitish gray lines, which were all converted to shared streets, and then icons that were converted to those specific multimodal corridor points. Does that?
We could recheck the map for you. Was it Marvick? I'll give you.
I can, I guess, share my screen.
Yeah. Okay. So that's in terms of where our Poodle points are placed. So that map shows specifically where we decided to place them, just based on proximity again to transit, plus 15 access, green space, and of course taking into account our iterated outputs of what the volumes are when we include those AVs. So we used, like you can see kind of on there, we used 6th Street as a specific case study, along with 8th Street, 6th Ave with a case study, 10th Ave and 8th Ave. Yeah, so that's the locations of our Poodle points. Does that make sense?
Thank you. We have another question. I think this is for the second team. Can you explain what variables are involved in the Wells-Rayleigh equation for COVID-19? For COVID-19 infection, is your scope looking at COVID-19 infections while in the train station, or do you include COVID-19 infections while people are on the train? By the way, the model is very cool. Great work.
So thank you, first of all. And if you could give OG presenter again, just for visual of the equation, so I can kind of describe the variables. Great. So for instance, P masked is just the probability that a susceptible person wearing a mask is infected. And P non-mask is the probability that a susceptible person not wearing a mask is infected. And then the variables within the equations themselves is just D infected, comma mask is the number of people who are infected and wearing masks. And no mask is just the people who are infected and not wearing masks. Then we have FM and RM, which both represent the percentage of particles captured by masks, both inhalation and exhalation. And P is the breathing rate per person. We had an average. And Q is the quanta generation rate. It's not a physical unit, but it captures the infectious particles in the air. And then Q is the capital Q is the room ventilation rate of clean air entering the system. So those variables gave us the full picture, and it mostly models the train station. It could be applied to the train car, but because of the limitations of our simulation software, we couldn't really model the interior of the train car fully with it. So it is, for the most part, towards our simulation, towards our train station simulation. Thank you for your question.
Great. I don't see any more questions coming in. Just give it another minute to see if we have any more questions. Doesn't look like it. Well, thanks again to both groups for their presentation. And these are very impressive and innovative ideas you are coming out of these bright young minds. This is probably where the future is heading to. And so if you have any more questions that you just thought of and would like to stay for the network, we'll be leaving this platform open for another 30 minutes and you can stay and chat. Other than that, thank you all for joining us today, and this marks the end of this webinar. Thanks again.